In here, we'll just try to look back into Laplace transforms of derivatives. The step functions, I'll introduce to you the step functions, basically the piecewise functions. All right, so this is just to recall what we had last time, the Laplace transforms of the derivatives. So you can see in here the same problems as we had last time. So going back here, you have a second derivative of y plus a squared y is equal to 0. And then you're given conditions. When x equals 0, y equals 1. And then when x equals 0, the y prime is equal to 0. So expanding this one, this is s squared ys minus sy of 0 minus y prime of 0. So the first three terms correspond to your y double prime. And then this one, since this is not a derivative, it will just be y of s. So a squared y of s is equal to 0. And then what we do here is we try to plug in whatever initial values provided here. So the y sub 0 becomes 1, y prime of 0 is 0. Therefore, it will end up being this second line. And then what we do here is we factor out the y of s. So you'll end up having s squared plus a squared minus s is equal to 0. Transpose the s and then put this underneath. You'll have this. You'll notice that this one is basically a cosine of at. So you have a function of s. What we want to get is the function of t. So you have the Laplace. I would want you to get the inverse Laplace of this. Okay. So for this second example, you'll notice there's a y double prime, y prime, and y. So for this one, you'll have the first three terms. For the y prime, you'll have the two terms there. And then here, it's just this one. And then similarly, you apply the conditions given, the initial values. Cancel whatever you can cancel. However, you'll notice that on the right side is expressed as a function of t. So you basically apply the Laplace to get the function of s. Now that everything is in terms of s in here, maybe you can do some, algebra to it, just like partial fractions. So you'll separate them and then individually, it becomes easier. And then you can apply the inverse Laplace to get the functions of t. All right, so on. Now, for the actual lesson, we'll be having this. The step functions, basically, the Laplace transforms of Heaviside functions. So if you may ask, where is this applied to? Typically for control systems, like for process control, for the designs of those automated systems, you'll be using this. So all of us in engineering, this one will be helpful. For example, this is an example of a piecewise function. So you'll notice there are three functions, f1 of t, f2 of t, and f3 of t. So for example, this is a signal. Let's just say time. When time is equal to 0, the signal is switched off. And then there's nothing. However, when time is equal to a, the function here is switched on. However, when the time is equal to b, function number 1 is replaced by another function, function 2, up to time is equal to c. However, when time is equal to c, this function is switched off and it's replaced by another function. So what's the representation of that one? So it can be represented by y of t is equal to f of 1. So f1 of t from a up to b. Now, when time is greater than b but less than c, it's replaced by function 2. When time is greater than c up to infinity, it's replaced by function 3. So how do we draw and how do we write those functions? For example, this is the unit step function defined by alpha. So the Heaviside step function is represented by alpha of t, or basically function of t here, is 0 when time is less than 0. So it's just like a switch. So when it's switched on, the amplitude here is 1. Of course, when it's off, it's 0. And sometimes it's represented by these letters in the books: capital H of t, U of t, theta of t, alpha of t, and capital U of t. Basta you know that they are unit step functions. So sometimes unit step functions, you have multipliers, but then sometimes it also shifts. For example, here, C shifts to the right. So you can say here that up to time equals C, there's nothing. But then when time is equal to C, that's when you switch it on. So you can say here alpha t minus C, so it's like shifting. So there's 0 when time is C, so it's like C minus Z, that becomes 0. But then if it's greater than C, there is a signal. Okay, look at this. For this function t minus C, alpha t minus C. So that means initially there is nothing. And then afterwards, whatever the function is, whatever the value of the function is, when time is greater than or equal to C. So I'll give more example. This is what you call the second shifting theorem. So this one, the important thing here, the one I use is actually the yellow one, because this one's look a bit more complicated for me. So I use the yellow one. So that's the second shifting theorem. So as I said, for Laplace, we have the first shifting theorem and the second shifting theorem. What's actually important here are these ones. You'll notice that there is the shift in here. That shift there is actually represented by this one, the e to the negative cs, that one. That's actually the shift of this one. You're given 2.5, so that's the multiplier to the amplitude, times alpha t. So that means when time is equal to 0, there's nothing. However, when time is greater than or equal to 0, so this one activates. It becomes 1 times 2.5, so it becomes 2.5. So how's the drawing? When time is less than or equal to 0, or less than 0, it's this. However, when time is greater than or equal to 0, it becomes 2.5. I hope you can follow. Now, look at this. The function t squared, you know that y is equal to t squared is a parabola. So some of you might ask, here, some of you might say, it's just a parabola. Yes, it's a parabola. However, it says there that alpha t. So you notice there's nothing there. T minus, you can say that that t is the same as t minus 0. So meaning, before 0, there's nothing. So what I would do here is, possibly, I could erase the left side. However, as time becomes greater than or equal to 0, there exists the graph. So here you can say there's nothing at the left side of the graph. There's no signal. However, as you get from 0 onwards, there exists the parabola. Now, another one. It's, some of you might say it's similar, sir. What's new in here? So just like last time, I'll just draw it. So let's just say in here, I have the parabola. Let's just say this is 1, this is 2, this is 1, this is 2. It says there, it is the equation of the parabola. However, it will activate only when the time is greater than or equal to 2. So some of you might say, where's that? That means I'll erase this portion until 2. So that means only that one, only whatever's left in here will be part of the graph. So you can see it here. There's nothing until it reaches 2, and then there's actually a jump because only that portion above will be left. All right. Next, y is equal to t minus 2. Some of you might say, sir, there's no alpha. Yes, Eddie, that's just a parabola. However, t minus 2, so the vertex would be in here. It's the whole parabola that shifted. Unlike earlier, the equation is just t squared. It's not t minus 2 squared. So the original equation would give us this parabola. However, due to the alpha, everything was switched off until time equals 2. So that is what you'll be seeing. Whereas in this case, there's no alpha. So that means the whole thing should be shown. Because you need to know how to read graphs. So in here, t minus 2 squared. So what's t minus 2? Okay, it's this. Alpha t minus 2. So meaning it will only activate when time is 2. So earlier you saw that the t minus 2 quantity squared is parabola opening up. So let's draw that. Something like this. However, it says there, when alpha is t minus 2. So for that, everything before t minus 2, you will not draw. There's no signal. So it's just 0, and then it goes up. Next, 2.5 minus 2.5 ut. Oh, now, we're used to seeing 2.5 ut, but then there's a 2.5 now. So that means initially, there was a signal even before there's time equals 0. So initially, there is signal of 2.5. That's why you'll see it there. But when time is greater than 0, you will subtract that 2.5. So it's the opposite. You understand? There's a minus. So sort of like initially I have that, and then when time is 0, this one will activate. You will say, when time is greater than 0, this u will become 1 times negative 2.5. Therefore, it's minus 2.5. Where will you subtract it from? From the 2.5. That's why it's the opposite. In here, initially you have t squared. So you have a parabola. And then when time equals 1, so here, I'll draw it first. When time is equal to 1, let's just see in here, I will subtract the parabola. So it's this one that will disappear. You understand? So on the left side, you have t squared. And then after time equals 1, you will cancel that graph because you will subtract the t squared. So you'll end up only up until time equals 1, and then it becomes 0 signal. I know this could be a bit confusing. So let's try drawing. You have an alpha when time equals c. So let's just say this is c. This is letter A. Okay. When time is less than c, so let's just say 0. Do you have anything? There's nothing. However, when time is equal to c or greater, will there be anything? Yes, it's equal to a. So that means from the left side of c, you won't be able to read anything. However, as you increase, you know that time is c onwards, you will be able to get a. I hope you can follow. Now, this one, the time element is 2. All right, so 1, 2. And then the amplitude is 3. So it says there, 3 alpha t minus 2. So originally, you have 0 before time is equal to 2. So before time is equal to 2, you have this. But as time is 2 onwards, greater than or equal to 2, that is your graph. That's a bit interesting. You know that the graph, what's the graph of y equals t? You know that it's just just like y equals x, it's this. It will only be present when t equals 3. So when you say 1 is 1, 2, 3, it's this, right? So you can say here that, how do we graph that? 1, 2, 3, you'll be able to see 3, 3. Initially, you don't have anything. But when time is equal to 3 onwards, it becomes that. In this case, you will cancel that portion because there's nothing before 3. So what will be the answer in here? Here, it's 0, and then it becomes t. All right. Number 4, you saw instead of t alpha, now you see a t already in there. So what does that mean when there's already a t? That means initially I have the graph already, right? And let's just say, let's take it from 0. There's already the t in there. However, when time is equal to 3, let's say that's the 3. This is the 3. After 3, you subtract the t. So it becomes 0. So that's t. When time is less than 3, t, and then this becomes 0. So some of you might say, sir, does it extend? It's okay to extend it. It doesn't really matter. Next, it's t minus 3. Let's just say y equals t minus 3. When t equals 0, y is negative 3. When y is 0, t is positive 3. So you know that the graph looks like this. However, it says there, the whole expression in here is attached or shifted by 3 units. So that means if the whole thing is shifted, initially it doesn't have anything. So that means time is equal to 3. I'll erase everything here prior to 3. So what would the graph look like? 1, 2, 3. That's when it increases. Prior to this, everything is 0. So here, t minus 3 when t is greater than or equal to 3. But then prior to that, there's nothing here. This one is a bit tricky because it says here, initially you already have a graph. And then there's alpha t minus 3. So maybe we can rearrange this. T minus, on top, it's just t. At the bottom, it's t minus t minus 3. So that becomes 3. They will cancel out. So what would the graph look like? Initially, you have a graph t. However, as you reach 3, 1, 2, 3, magiging 3 lang yung value niya. The line t cancels out, as you can see in here, and then it will just be replaced by 3. So this is y equals 3, so x equals 3. So this is the shape of the graph. Now, given the other way, I'll be giving you the shape, but then you will have to give me the Heaviside function. So let's say this one. I can say that for this one, my y of t, or basically your equation of y, is let's just say that is any function of t, because according to this one, any function of t. So you can see here that initially, there's a function of t when time is less than b. But then there's no more function when time is greater than or equal to b. So how do we write this? I can say that y of t is basically f of t, right? There's f of t already. But then I will remove that graph. So I will subtract f of t alpha t minus b. So you will subtract the graph. Sige, let's go to number 2. Number 2, what you have here is you don't have anything yet when time is less than a. But then the graph of the function of t exists when time is greater than or equal to a. So I can see here that initially I don't have anything. And then I will add, because there will exist the graph when t is greater than a. So t minus a. So if you want the final function, you can say y of t is basically f of t alpha t minus a. The 0 there, you don't mind that because it's just 0. So this is my working function. And then later on, after this, that's why I ask you to read on the second shifting theorem. I'll teach that to you. It will be helpful once we evaluate this one. Now look, the third one, you don't have anything when time is less than a. So sorry, this one, let's just fix this. This one is a, that's b. Let's just erase that. Okay. So initially, there's nothing when time is a, and then there exists the function when time is greater than or equal to a, but less than b. And then there's no function again when time is greater than or equal to b. So how do you write this? You can say, initially, I don't have anything, and then there will exist the function when time is greater than a. So alpha t minus a. And then you will remove the function when time is greater than b. So I will remove the same function when time is greater than b. So the y of t that you have eventually is f of t alpha t minus a minus f of t alpha t minus b. This is your working function. Next, you will notice that this is the graph of your f of t, right? Remember that f of t is this shape. So I can see here that y is basically 0 when time is less than b, but y is f of t minus b when time is greater than or equal to b. So some of you might ask, why is it f of t minus b? Why not just f of t? Look at the shape. This is f of t, right? So if I were to draw it like this, let's just say that one. And then I would say, this is your time A, this is your time B. This is my final graph. Let's just say here. It's basically the same shape. The whole thing is the graph of your f of t, right? This thing is your f of t. I can see here that y is 0 when time is less than b, but y is the function of t when time is greater than or equal to b for this curve. But then you'll notice that what I gave you in number 4, the whole graph is the one that shifted, not when it activates, the whole thing shifted. So I can say that y is 0, and then I will add the whole thing shifting f of t minus b alpha t minus b. So let's just remove the unnecessary. F of t minus b alpha t minus b is the working equation. So for the one underneath, what would be my working equation? Simply 0 plus f of t alpha t minus b. Therefore, this is f of t alpha t minus b, which is different from the one on top. The one on top incorporates the whole graph. Here, only part of the graph is activated when time is greater than or equal to b. And then, yeah, so here, that's when we will apply the second shifting theorem. That what will happen is this: you will have something like this, and then you apply the second shifting theorem, and then sometimes you will be given graphs. You should be able to apply the concepts and then get the inverse Laplace or get the Laplace depending on what's needed. And then eventually you might ask, sir, where do we apply that on differential equations? In here. For example, solving more than one d using Laplace transform. So we will be giving you the differential equations. So you will apply the derivatives of the transforms here. And then after that, you will apply the Heaviside and the shifting theorems. Okay? So I will end my lesson in here.